Let's talk about bond energies and bond length. We can use individual bond energies to estimate enthalpy changes in a reaction. So the enthalpy of a reaction or the heat of a reaction. These are estimates, but we can get this fairly simply, and so it is useful. So what is bond energy? The bond energy is the energy needed to break 1 mole of that sort of bond in the gas phase. Bond energies are always positive. It requires that you put energy in. It's an endothermic process in order to break the bonds. So it's always positive. A bond is stronger if it takes more energy to break. So that kind of makes sense. I mean, think about breaking a twig, right? You can snap that pretty easy. A larger branch, you're going to have to apply a lot more force, maybe break it over your knee. It's going to be harder. The branch is stronger, you have to exert more energy to break it. So a more positive bond energy means a stronger bond. So we could represent the bond energy like this, taking HCl in the gas phase and breaking that single bond between the hydrogen and the chlorine. We're going to end up with a hydrogen atom and a chlorine atom. The enthalpy change here is 431 kilojoules. And that is for 1 mole of this compound. So all of these energy amounts are for 1 mole. So compounds that have stronger bonds tend to be more stable, because in order for HCl to react, you have to break the bond. And if the bond is hard to break, it's not going to react very easily. So bond energies vary. And so what we do is we look at an average bond energy. So they've measured bond energies in lots of different compounds, and they've compiled all of this data. You can find it online. There's a table in your textbook, or the CRC, that big old fat book that we looked up water density in, that has just pages and pages of bond energies. And it's an average, because let's look at this carbon-hydrogen bond. So the strength of that, or the amount of energy needed to break a carbon-hydrogen bond, depends on what molecule that bond is in. If that's in methane, and we're looking at the carbon-hydrogen bond, it's going to take 438 kilojoules to break. If that carbon-hydrogen bond is in this molecule, trifluoromethane, it's going to take 446 kilojoules. Tribromomethane, 402, and trichloromethane, 401. The exact amount of energy needed to break the carbon-hydrogen bond is a little different depending on what molecule that bond is in. So what we do is we average the bond energies for that bond in a bunch of different compounds. So the average bond energy for carbon-hydrogen bond is 414 kilojoules. And we're just going to use the average. These are estimations of heats of reactions. They're not precise. Double and triple bonds have higher bond energies than single bonds, because that would be like breaking 2 sticks or 3 sticks, right? It's going to take more energy to break them. So here is a table of bond energies from your textbook, table 9.3. So these are all average bond energies, and most of them, there's just one value. There's the exception here is the carbon-oxygen double bond. The carbon-oxygen double bond is 736, except in carbon dioxide, it's 799. It's down there where I can't point. That exception is listed because it is significantly different from the average, and carbon dioxide is a very commonly encountered molecule. You do not memorize these bond energies. You just go look them up. If you need them on an exam, they will be provided either in the question or as a table that you can look at. Okay? So how do we do this? Well, if you break a bond, it's an endothermic change. You have to put energy in. Forming the bond is the opposite. If it takes 100 kilojoules to break the bond, when you make the bond, it releases 100 kilojoules. So it's just the opposite sign. So breaking bonds is positive, making bonds is negative. So to estimate the heat of reaction, we're just going to add up all those changes. Positive values for bonds being broken, negative values for bonds being formed. So here's a relatively simple example. We're going to react a methane molecule with a chlorine molecule. So there are bonds here, and we need to break this chlorine-chlorine bond, and we need to break one of these carbon-hydrogen bonds. So that's going to require us to put energy in. We're going to break this chlorine molecule into 2 atoms. We're going to pull 1 hydrogen off the methane. So we can look those values up and figure out how much energy we're putting in. Then we're going to make some bonds. And that's going to be a negative change. It's going to be releasing energy. So we're going to have a bond forming between chlorine and this loose hydrogen. And we're going to have a bond forming between the other chlorine and the carbon on this thing. And so we're going to have 2 bonds forming. So you have positive numbers for the bonds being broken and negative numbers for the bonds being formed, and you put them all together, and that gives you an estimate of the heat of reaction. So we often say that energy is stored in chemical bonds. That's kind of not quite right. Breaking a bond requires energy. So how is energy stored in the chemical bond? Well, an energy-rich compound that has high chemical potential energy can undergo a reaction in which weak bonds are broken and strong bonds are formed. The energy actually comes from the forming of bonds. So compounds that burn well, like methane and octane and various flammable things, they have some weak bonds that can easily be broken, and then those can form new, stronger bonds, and that's how we get the release of energy. Okay, a potential future fuel is methanol, CH3OH. Write a balanced equation for the combustion of gaseous methanol and use bond energies to calculate the enthalpy of combustion of methanol in kilojoules per mole. So the first thing is write a balanced chemical equation for this burning. Well, what is the other reactant when something burns? Oxygen. So we have CH3OH, and it's going to react with oxygen. This compound has carbon, hydrogen, and oxygen only. What are the products? CO2 and H2O. So we've got enough oxygen, and we're going to get carbon dioxide and water. Where you end up with carbon monoxide and people die in their homes is when you have a gas-burning appliance that is not getting enough oxygen. If there's not enough oxygen, then you're going to end up with carbon monoxide, and that can be very tragic. But here we've got plenty of oxygen. So we need to balance this. We have 1 carbon on the left and 1 carbon on the right, so that's cool. We have 3 plus 1, 4 hydrogens here, and only 2 over there. So if we put a 2 in front of the water, we have 4 hydrogens on each side. Now we've got 2 oxygens plus 1. We've got 3 oxygens over here and 4 oxygens over there. That's what I call the odd-even problem. So we've got 1 oxygen in that one and 2 oxygens in this. And here we have 2, and 2 times 1 is 2. You can use fractions here, but most students don't like that. So what we can do is we could just double all the coefficients, and that'll give us even numbers. So if we double the coefficients, we're going to put a 2 here. This is the one we're messing with, so we're going to leave that one blank for now. We're going to change this to a 2, and we're going to change this to a 4. So now we have 4 oxygens here, 4 oxygens there, 2 oxygens here, and then we can mess around with this and not mess up the hydrogens or the carbons. So we have a total of 8 over here, and 2 plus 2 is only 4. We need this to be 6, right? 2 plus 6 will give us 8, so we'll put a 3 in there. So that's a review of balancing equations. So let's get rid of our scribbles here because we don't need those. So now we need to use bond energies and calculate the enthalpy of combustion. There's 2 ways you can approach this. You can just figure out what bonds are being broken and formed, because some of the bonds might not be broken. That involves too much thinking in my book. So what I like to do is say, well, what if we just took everything apart? Let's figure out how much energy it would take to break everything and then to make all the new bonds. Okay, so instead of taking the Lego constructions and just taking these few blocks off and moving them around, we're just going to take all the blocks apart and start from scratch. I think that's the more straightforward. So what we have to do is we have to look at what bonds do we have in these molecules that are getting broken. So you really need to have Lewis structures, because this O2, I know it's a double bond, but if you don't think about it much, you might think it's a single bond, and then you're going to end up with the wrong answer. So let's do this in a different color. So the carbon is going to be bonded to 3 hydrogens, and we have an oxygen and a hydrogen over there. And then there would be lone pairs just to fill things out. It's not absolutely necessary to look at the lone pairs, but in order to get a good Lewis structure, you're going to need those. And then over here for CO2, the carbon is double bonded to the oxygens. You would take more time figuring this out, but it's not the point of this problem, so I'm not going to go through all of that. Those are the Lewis structures for the compounds involved. So we're going to look at the different types of bonds that are being broken. So here we have carbon-hydrogen bonds. Always do that. So we've got carbon-hydrogen bonds being broken, and we have a carbon-oxygen single bond, and we have an oxygen-hydrogen single bond. And then we also have oxygen-oxygen double bond. So I'm looking at all the different kinds of bonds in my reactants. Does that make sense? Now let's figure out how many there are. We have 3 moles of oxygen. Each mole of oxygen has 1 mole of double bonds. So that means I have 3 moles of oxygen double bonds. So 3 times that. How many moles of oxygen-hydrogen bonds do we have in 2 moles of methanol? 2. Because each molecule has 1 of those bonds. So if we have 2 moles, we're going to have 2 moles of bonds. How about this carbon-oxygen bond? Also 2. Now what about the carbon-hydrogen bonds? 6. In this 1 molecule, there are 3 carbon-hydrogen bonds. In 1 mole of this, there would be 3 moles of carbon-hydrogen bonds. We have 2 moles. So we have to multiply that, and that's 6. Questions yet? It's just a lot of keeping track of stuff. It's just a bit tedious. So then let's list the different types of bonds that are present in our products. So we have carbon-oxygen double bond, and we have oxygen-hydrogen bonds. There's only 2 kinds over there. List the kinds, then figure out how many. Well, 1 molecule of carbon dioxide has 2 of these bonds. So 1 mole would have 2 moles of bonds, and we have 2 moles, so we've got 4 moles of that one. Over here, each molecule has 2 oxygen-hydrogen bonds. That means 1 mole would have 2 moles. We have 4 moles of that. So 8 moles of oxygen-hydrogen bonds. Now we need to know what are the bond energies for these different things. I don't think I have a table coming up. No. So we have to go back to this table, and I'm going to cheat and use the chalkboard. So we needed carbon-oxygen double bonds, and that's in CO2. So that's the 799. And we had oxygen double bonds, and so that's right here. Yeah, it's 736, except if it's CO2, and this time we do have CO2. So oxygen double bond 498. We had oxygen-hydrogen bonds. Those are under hydrogen 464. Let's see, we had carbon-hydrogen bonds. That's over here. No, up here. Hydrogen-carbon 414. And we had carbon-oxygen single bond, 360. Did I miss any types of bonds? We'll find out. Okay, so let's go back to our list here. So carbon-hydrogen bond is 414 kilojoules, and we have 6 of those. So 6 times 414. These are positive numbers because we're breaking these bonds. Then we have the carbon-oxygen single bond is 360 kilojoules to break, and we're breaking 2 moles of those. Oxygen-hydrogen is 464. We're breaking 2 moles of those. And the oxygen-oxygen double bond in CO, no, that's just oxygen-oxygen, never mind. 490, and we've got 3 moles of that. So I'm leaving the units out here because the slide already gets really crowded. The unit on this is kilojoules per mole, and we've got 6 moles. So the units work out to kilojoules. So we add all of these together. I need a calculator for that. 6 times 414 plus 2 times 360 plus 2 times 464 plus 3 times 490 equals 5602 kilojoules. That's the amount of energy we'd have to put in to break all the bonds. Okay with that? Over here, we're forming bonds. Forming bonds releases energy, and so these are going to be negative numbers. So carbon-oxygen double bond. When you break that in CO2, it's 799 kilojoules, but here we're making it, so it's negative 799 kilojoules. And we've got 4 moles of that. The oxygen-hydrogen bonds are minus 464. It's negative because we're making the bonds. Making bonds releases energy, and there's 8. So We add these together. 4 times negative 799 plus 8 times negative 464. This gives us negative, 6908 kilojoules. So we have to put this much energy in, and we get this much energy out. It's a little bit like a monetary investment, a financial investment. You have to put some money out there, but then you get back more than you paid in. So the difference, well, the total here, 5602 and negative 6908. Yep, minus 1306. So as this equation is written, we're going to get minus 1306 kilojoules. That's for 2 moles of methanol. What does the question want? Combustion of methanol in kilojoules per mole, kilojoules per 1 mole. This much energy came from 2 moles of methanol. We have to divide by 2. So we've got negative 1306 kilojoules coming from 2 moles of methanol. We divide by 2, negative 653 kilojoules per mole. Any questions? Yes? Yeah, the product numbers are always going to be negative because here we're making bonds. So, and this goes back to Hess's law, where it doesn't matter the process, it's just the energy change from beginning to end. And so what I'm imagining as the process is we're breaking all the bonds in the reactants, so that's putting energy in, and then we're forming all of these bonds from scratch, so we're releasing energy for that. Okay, this is the sort of problem that will be on the exam. And it would be one of the show your work problems. Because this last piece of dividing by 2 is a frequently overlooked thing. And I hate this to be a multiple choice where you overlook that one little thing and you get the whole problem wrong. When it's show your work, you can get partial credit, and you do all of this stuff correctly, and you just forget to divide by 2, you probably just lose 1 point out of 4, 5, or 6 points. Any questions? Bond lengths. Here again we talk about averages. An average bond length is the average length of a bond between 2 particular atoms in a large number of compounds. So just like we average the bond energies, we average the bond lengths. Double bonds have higher bond energies. They're stronger. They also tend to be shorter. Triple bonds are shorter than double bonds, and they are strongest. So triple bonds are stronger, double bonds are in the middle, and single bonds are the weakest. And we look at the bond length for carbon bonds. A triple bond's 120. Carbon double bond is 134, and a carbon single bond is 154. And we see that the bond strength, or the bond energy, is highest for this shortest triple bond. So the closer these things are together, the harder it is to break them up. Longer bonds are generally weaker. Of course, there has to be exceptions. Oops. So here's a table of average bond lengths. And again, these are not things you would memorize. You can see here carbon-nitrogen bonds, single, double, triple. The length of the bond goes down. These are measured in picometers.